The topic now is integration by parts, and this is, again, just looking at more techniques of integration. What are other ways to solve more complex integrals? So, the overview is that this is a modification of the product rule. So we look at the product rule and then we see how that's going to give us, some fancy integral rule. So if we start with our h of x equaling to f of x times g of x, that means that h prime of x will equal to f prime of x g of x plus g prime of x times f of x. That means that when we rewrite that, or when we integrate both sides, we get that the integral g prime of x dx is equal to the integral of f prime of x g of x plus g prime of x f of x dx, which means that h of x is equal to, or h of x plus c is equal to the integral of f prime of x g of x dx plus the integral of g prime of x f of x dx. So all that we did was we showed the product rule, integrated both sides, and then we're going to start cleaning up, simplifying, rewriting things like this. We only need c on one side. We only need one c ultimately, so I'm going to kind of play a little bit fast and loose. But if we rearrange this, we can get the integral of f of x g prime of x dx is equal to h of x minus the integral of f prime of x g of x dx. So I moved the g prime f of x, or sorry, the f prime g of x to the left-hand side. And then because I know that I'm going to end up getting a c from this integral, I left off the c that was already here. And that's because, remember, it's just saying at the end of the day, we should have an arbitrary constant added on that could get, derived out. So I know that this right here is going to produce a c, so I've left it off, I've ignored it. And then we can also clean this up by saying u equals f of x and v equals g of x. So therefore, this ends up giving us kind of the standard way that we talk about integration by parts, which is a formula that you kind of memorize, and then when we get used to using it, you'll understand what it does. But the formula is u dv equals uv minus the integral of v du. So that's because if you take the derivatives of these, you'll get that du dx is equal to f prime of x. So in other words, du is equal to f prime of x dx. And by the same token, dv is equal to g prime of x dx. So I'm plugging it in. F of x is u, g prime of x dx is dv, h of x is just f of x times g of x, so u times v. And then the integral of g of x is v, and f prime of d of x is du, and so this right here is the way that we typically present the integration by parts. And the idea is we want to pick something, we're rearranging the integral into a different integral that might be easier to solve. And it isn't immediately obvious where we use this, but as time goes on, you'll develop an intuition for it, get a feel for when to try it and see if it helps you out. So, like I said, you'll develop an intuition with practice, but generally what you should be looking for is that your u should get quote unquote simpler when you take the derivative of it. And you also should be looking for your dv to not get more complex. So you should look to see that your function, looks like part of it will clean up and part of it won't get worse. So when we're talking about complications, things that make a function more complicated, we're referring to the power or order of magnitude. Of the function. So for example, all polynomials get simpler when deriving, right? If you keep deriving polynomials, what happens? So x cubed becomes 1/3 x squared. It gets simpler. That exponent gets smaller and smaller and smaller. Conversely, e to the x, sine of x, and cosine of x, when you take the derivative of those, they don't get simpler. They kind of stay the same. But on the flip side, when you integrate e to the x, sine of x, cosine of x, those pretty much stay the same when you integrate them, right? The integral of sine of x is just going to be negative cosine of x. The integral of cosine of x is just going to be sine of x, right? It doesn't look a whole lot more complicated. It's a little different, but it's not a lot more complicated. So all polynomials get simpler when deriving, and things like e to the x, sine of x, and cosine of x, they kind of stay the same complexity. They don't get worse over time. So in the next couple of videos, we're going to look at a bunch of examples of different situations and ways that this plays out.